All right, so chapter 6, part 4, partial fractions. If you're a junior, take one of these and pass it. If you're a senior, just pass it. Those are for juniors. This has to do with your pictures, senior pictures next year, I think. Okay, so partial fractions. What the heck do they mean by partial fractions? Well, that's when you rewrite a rational expression as multiple lesser degree rational expressions. So the goal is to factorize the denominator completely and rewrite this rational expression as a sum or difference of other rational expressions which have those fully factored denominators as the new denominator. Any lower classmen in the back here? None? Okay. We have some extras. Yeah, that's a good observation, sir. And then partial fraction decomposition is just the process of going from a normal rational expression. So this will be new. And these are the factors of the original denominator. So there's kind of a process, and there's several different scenarios that we'll run into. And each of them work out a little differently. So these are almost, and they work out so differently, they're almost kind of like discrete problems. So these are only loosely related. Oh my goodness. I hate that Coretta. You get it too full, it does it. And our little janitor works hard to keep the floor clean. Hate to make his little life more difficult. There we go. All right, so partial fractions and partial fraction decomposition. So we're going to start out with distinct linear factors. So this means the denominator can be fully factored into a series of linear factors, and none of them are repeated. So denominator is a greater degree and has only linear factors which are not repeated. So the denominator is a greater degree and it has only linear factors which are not repeated. That is this particular flavor of partial fraction decomposition. And this is the easiest type of problem of this sort. So what I'm going to say is the original rational expression is going to be equal to some sum of two rational expressions where the denominators are the factors of the original denominator. Like so. Yeah, distinct linear factors. Okay, everybody see where these two values come from? Don't need to explain that. Okay. So, and they're going to have some A and some B as their numerator. So these are just regular values, but for whatever weird reason, it's conventional to use a capital letter here, just like for a matrix, but it's not a matrix this time, just a value. Okay, so what we need to do is create a common denominator situation so we can find A and B. So in this case, I need to multiply the first by x plus 3 and the second by x minus 4. So there's a lot of action going on here. You'll see that. Man. That mask is just way too uncomfortable. I'm not going to fight that thing the rest of the day. That's not much better. Oh well. Hard to find one to fit my big head. Oh, okay, so continuing on. The next step, we're going to have common denominators. So I've got so when I have all common denominators, as long as I assume those denominators may never be 0, so I can say my restricted values, it's not as important here, but we'll go ahead and state them anyway. So as long as x never equals -3 or +4, then this is true. So as long as those denominators are never 0, the numerators can be set equal. Okay, so I'm going to simplify this here. And I've got two things going on. So this is so take a second and make sure you understand how I got that simplification. Oh my goodness, that one's even worse. So, and you might say, wait a minute, Mr. Sager, this is one equation, and we got A and B, two unknowns. How in the world could we ever solve that? Well, because we know A plus B has to match the coefficient of X. So we got different powers of X in these terms. And then this, I'll use a different highlighter color. And then this value has to be the same as the constant. You see how no matter what the coefficient of X is, it'll have no impact on the constant value. And no matter what the constant is, it'll have no impact on the X's value. Those are unlike terms. And so it's sort of two equations packed into one, if you will. So I know from this information that A plus B has to equal 1. In other words, this coefficient of X has to match this coefficient of X. And then 3A minus 4B has to equal -25. And I'm sure you've been wondering, what the heck does this have to do with the matrix? Well, here we are. Now we can apply a matrix. Because this is a system, right? So let's make our little RREF. Because when left to our own devices, that's what we like to use. So let's see what we get here. So we got 2 by 3. No. Yeah, 2 rows by 3 columns. And 1, 1, 1, and then 3, -4, -25. And we're gonna RREF that matrix. So it's given me
You didn't get T1 already.
oh, I got REF. Well, no wonder it was weird. Thank you, sir. Sometimes I click too fast. Did it again. Okay, hold on, we'll get there. Thank you, guys.
You can just do alpha B.
There we go. I was going too far, is what I was doing. Okay, so there we go. So -3 and +4. Meaning our original rational expression. So I'm just going to steal this right here so I don't have to rewrite it. And wow, that was unsuccessful. So originally here we had this, and now I know in place of A and B, I can write -3 and +4. And so this is my answer. Partial fraction decomposition of that original rational expression. So that is the scenario that is appropriate for when you have a denominator with a greater degree. So in other words, this is higher degree than this. And only linear factors that are not repeated. So that's the only type of flavor of these problems you can apply this particular technique to. Now let's talk about example 2. So this is when you have an improper rational expression. So this is, and the difference here is the numerator will have equal to or greater degree. So the numerator has greater than or equal to degree when compared to the denominator. Jesus, I'll get it right in a second. So partial fraction decomposition of this, we have the same degree in the numerator as the denominator. So the numerator is second degree, the denominator is second degree. So what we have to do first is the division algorithm. So take the denominator and set it as the divisor outside the house. The numerator and set it as the dividend inside the house. Plus 9x minus 4. So we're going to divide this. So x squared into -2x squared goes -2 times. And if I multiply, you guys remember this back in chapter 2? -2 times x squared is -2x squared. -2 times -x is +2x. And then we subtract away. And I get 0 plus 7x minus 4. Now x squared won't go into a single power of x. So this is the remainder, and this is the quotient. And so remember, I can rewrite this as the quotient plus the remainder over the original divisor. So this is -2 plus 7x minus 4 over x squared minus x. So that first value comes, the first step when you have the numerator greater than or equal to degree to the denominator is long division. So once I get here, I can now apply the same process I used on the first problem. So we've got -2 plus, and I'm going to ignore the -2 for a moment because that'll be confusing. So I'm only going to concern myself with this rational expression part. So 7x minus 4 over x squared minus x is going to be equal to something plus something else, where the denominators are x and x minus 1. Take a second, make sure you know where I got those values. Let me know if you know. Okay, good deal. So x and x minus 1 are the factorization of this denominator. So now we're ready to rock and roll. So 7x minus 4 over x squared minus x equals a times x minus 1 over x times x minus 1 plus b times x over x minus 1 times x. So I've multiplied top and bottom to make the denominators match. And now I can say, as long as I make sure x is not equal to 0 or 1, that's 7x minus 4 equals a times x minus 1 plus b times x. So 7x minus 4 equals ax minus a plus bx. 7x minus 4 equals a plus b times x minus a. So I know a plus b has to equal 7. And I know that -4 has to equal -a. So, don't need a calculator for this one, do we? That's pretty straightforward. Look at this and tell me what A and B are, Cody.
A is 4 and B is 3.
4 and 3, very good. See how you know 4 from this? And then if you plug it in here, it's obvious that B has to be 3. So you could use a matrix if you really wanted to, but that's a system that you should be able to look at and determine the values of A and B. So once again, we'll go back and steal our earlier representation to save ourselves some work. Now, A and B are not interchangeable. So you got to remember where you had A in your original formulation. Question, Caitlin.
So when you were doing the work, why did you do, I may have missed it, you may have explained it, but why did you do minus A?
Whatever it appears to be here. You see how it's negative?
Mhm.
So that negative has to be considered.
Okay.
So minus A on the right is equal to -4 on the left. So if I didn't have the negative sign here, it would be a sign error.
Okay.
Yeah, so whatever it is in the algebraically derived equation, it must be in the system you develop.
Okay.
So if you remember the previous problem, I had -4b. So you see how that became minus in the equation and a -4 in the matrix. So the same sort of logic forces us to use -a here. Okay, good question. Other questions? All right, good job, guys. Don't hesitate to be your own self-advocate. But that isn't the whole thing, right? Remember, we had the -2. So our full answer is going to be the original, which I won't bother to write, I'll just let this stand in for it, equals -2 plus 4 over x plus 3 over x minus 1. So there's the original equal to a partial fraction decomposition. Questions about that? Anybody? Okay, so on to the third scenario, which is when you have a denominator that has different factorizations going on. So if I look at this denominator and I start factoring it, first of all, the GCF is an x. And then after I factor this perfect square trinomial quadratic, I get, so you see that we have a factor with a multiplicity greater than 1. In other words, it's to the second power. So even when it's fully factored, it's to the second power. So when you have a factor that is repeated, so this particular technique is going to be when you have repeated factors in the denominator. So repeated factors in the denominator, we must account for all powers of it, up to and including the final power. So in this case, there's only 2 powers. So I'm going to say x because that's our first factor, not repeated. We don't have to worry about it. But then I need to say x minus 2 and then x minus 2 squared. So when you have a repeated factor, the little bit of weirdness that comes in is I need a term for each power of that. So it's to the second power as the highest power. So I need 1 and then 2. If it were cubed, I'd need 1 and then 2 and then 3. So that's kind of a weird situation. And I need to account for so this is a repeated factor. This is not going to be the exact same strategy as when you have an irreducible quadratic. So that comes later. So this is when you have a linear factor that's repeated twice. So this will have A, B, C. We don't know what A, B, and C are yet, but this is how we're going to set up our solution. Once again, we need to multiply everything by the missing factors from the denominator on the left. So for this, that's x minus 2 squared plus b, this will be x times x minus 2. And then for the last one, it's just x. So we're creating common denominators with this strategy. Fill the temperature rise. Somebody has turned the heat on. Most unfortunate. So if we multiply this out, we get A times x minus 2 squared plus B times x minus 2 plus C times x equal to that original numerator. But we have to say x could never equal 0 or positive 2, so let's keep that in mind. That was always the case because we can't equal it in this expression either, but we'll note it just for consistency's sake. All right, so let's simplify that to right side. So that's A times x squared minus 4x plus 4 plus B times x squared minus 2x plus cx. So I've got ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. And I just need to arrange these in standard form and I'll have my answer. Or my setup for my matrix, I should say. So I've got ax squared plus bx squared. And those are both the x squared terms. I've got three terms involving x. Minus 4ax minus 2bx plus cx. And then plus 4a. So once I've got all this figured out, I can develop my matrix. So I know a plus b has to equal 3 because they're both coefficients of x squared. And no action in the other terms can impact the value of x squared. And then minus 4a minus 2b plus c has to equal minus 5. And then plus 4a has to equal plus 4. So let's write those equations. So we've got a plus b equals 3. I've got negative 4a minus 2b plus c equals negative 5. And then I've got 4a equal to 3. Oh, 4, yeah, jeez. Thank you. All right, so now it's right. Let's do the matrix. All right, let's see. Edit. We want it to be a 3 by 4 this time. And 1, 1, 0, 3, negative 4, minus 2, 1, negative 5, 4, 0, 0, 4. Notice how I kind of set myself up for success by leaving these blanks here. The blanks just make it a lot easier to create a matrix. If we hadn't done that, then this would be a little more challenging. It's a good habit to get into. So let's try the RREFA again. I can just call the previous input. 1, 2, 3. Well, how easy is that? So A, B, C equals 1, 2, 3. So to write our final answer, we'll go back to that original formulation. replace A, B, and C with 1, 2, and 3. And that's our answer. And so remember, that process is necessary when you have repeated factors, repeated linear factors, not irreducible quadratics. Those are a different ballgame. So repeated linear factors, this is how it goes. So you must, first and foremost, identify the type of problem you're dealing with. So don't just mindlessly start doing what we did in example 1. Look carefully. See if the numerator is lesser degree than the denominator, or if it's greater than or equal to, because that determines whether or not you have to do the long division first. Then look at fully factorize the denominator. Is it discrete linear factors, or is one of them repeated? And then this final situation, which is, does it include irreducible quadratic factors? So if it has that, then it's a whole other ball.
On example 3, I assume the denominator was greater. We didn't do it.
Correct. It was to the third power. The numerator was to the second. So degree 3 on the denominator in example 3, degree 2 on the numerator. So we did not have to concern ourselves. If it had been other than that case, Clay, we would have done the division algorithm first and then proceeded with this. All right. So here's our, and I don't like that example. Let's see if I can. Well, I guess that's the only one we got. Okay, so x cubed minus x over x squared minus 3 quantity squared. So we got a couple things going on. They throw two things at us at once, and that's why I don't love it, is because we've got an irreducible quadratic, and it's also repeated. So we're going to need both powers of it. And because it is an irreducible quadratic term, I need a linear divisor. So I need two terms in the divisor, or in the numerator, so dividend. Cx plus d. So this case is when you have prime quadratic factors. You need this for the numerator. Two terms in each numerator. Ax plus b, cx plus d. For each of the prime quadratic factor denominators. Okay, so x cubed minus x over x squared minus 3 quantity squared. So we're now going to get a common denominator. And then over here we already have the common denominator, so we needn't worry about it. And I don't have to worry about division because, oh man, this is a 3. This is a 2 and a 2. These are less. No. If I were to expand the denominator, it would be to the 4th power. So this is a 4th degree denominator. This is a 3rd degree numerator, so we don't have to worry about long division in this case. But it can be tricky. Sometimes difficult to discern. So we're going to set the numerators equal now. There are no real solutions to that, no rational solutions to that denominator, but there are irrational solutions. So if you want to be super technical, I could say x can equal the square root of 3, plus or minus.
So why did the CX plus D already have the same?
You see how they match, Rachel?
Or like how, why would
Because there's no additional factors. So if there were an X out here or something, then I would have needed an extra term and I would also have needed to multiply this by X. But because there's nothing except for this irreducible quadratic factor of the second power, because I had to use its second power as a denominator of one of my partial fraction decompositions, it is already the same denominator.
Is there a time thing with that? Would you still need to put like EX plus X? Or would you
Yes.
just use-
Oh, no. If it were linear, you would just use a single variable. So if it had also a linear factor, you would use the same numerator that we used before. Good question. Other questions? Okay, so this is A, and because we've got two terms, it's like this. AX plus B times x squared minus 3 plus CX plus D. So x cubed minus x equals AX cubed, first times first, plus negative 3AX, outer times outer, plus BX squared, inner times inner, and then minus 3B, last times last, plus CX plus D. So I've got x cubed, and I'm going to write plus 0x squared just for clarity, minus x equals, and then I've got AX cubed, that's my only third power, and then for squared, I've got plus BX squared, the only squared term, and then I've got minus 3A plus C times X.
What's the minus 3B?
It'll come.
Okay.
I'm giving myself the maximum amount of room. Okay, so now minus, well, let's do plus minus 3B plus D, just so there's not a lot of sign confusion. Okay, so I've got A is equal to 1 because the coefficient of x cubed here is 1. The coefficient of x cubed here is A. So I've got a system where A equals 1. And then I've got B equals 0. And then I've got minus 3A plus C equals negative 1. So minus 3A plus C equals negative 1. And then for the last one, there is no constant term here. So minus 3B plus D equals 0. This is kind of a funky one. We use the calculator, even though you should probably be able to figure that out by looking at it. So here we got 1, 2, 3, 4 rows, 1, 2, 3, 4, 5 columns. So 4 by 5. And it is 1, 0, 0, 0, 1, 0, 1, 0, 0, 0. Negative 3, 0, 1, and 0, negative 1, and then 0, -3, 0, 1, 0. So the answer is A is 1 and C is 2. B and D are both 0. A is 1 and C is 2. So B and D weren't necessary, but we put them in there in case they weren't necessary in this particular case. All right, now let's go back to our original formulation, plug in our variables. So AX plus B is just 1, and CX plus D is just 2. It's, if you look, yes, 1X and 2X, I'm sorry. Yes. Yeah, because A times X, so A is 1 times X. Yes, I'm sorry. Should be that way. And 1X is easier to just write as X. There we go. Okay, so that's chapter 6, part 4. Questions about it? Okay. Your assignment will be this, if you want to take a second to note it down. It will, of course, be on Google Classroom. I mean, physically write it down, because I'm not going to leave it up here long. And I don't want to question what was that assignment later on, because I put it up.